Hello, in this video, we are going to revisit the linear programming problem that we discussed in class the other day. And I hope that by going through it again, it will help solidify exactly what we were doing, and that will make it easier to understand how this problem we're solving is different from subsequent problems that we will be solving. In this problem, we are maximizing the number of units sold, and then we have some constraints about, we know what the response rates are going to be, we know how much budget we have to spend, we know how many responses we hope to get, and there's a ratio between those. So we're trying to figure out how many customers to reach out to in each of, in this case, only 2 different categories of customers. And then this is adapted, taken from the example that we discussed, and the link is there. I mentioned in class that the original example, they're talking about providing coupons for people to take a weekend test drive. And in the example, which is obviously dated, they're talking about mailing out videotapes. And I talked about how that really was a thing back in the day. But I think what makes this problem interesting to think about is that it easily generalizes to many, many scenarios where we want to offer to people a sample. And we're deciding who is it worth spending money on sending a sample to. Back in the day, AOL used to mail out floppy disks or CDs or whatever. And now there are countless services that will send you packages every month. It could be educational, it could be wine, it could be food, shaving products, clothing, countless types of subscription services like this. And many other scenarios where we can imagine providing people, deciding which groups it's worth spending the money to reach out to give them a sample, because we believe that they will then become customers. And so that's the scenario that we're considering, which is widely applicable. This is my reorganization of all the text from the original website. And I've just separated it out into some bullet points. And it seems like there's a lot of information here, but a lot of it is really just helping us understand the scenario, and we'll work our way through this again. So again, the scenario is we're sending out, in this case, coupons for sample test drives. And we think that, well, the market research people have looked at current customers and then potential new customers. We think 25% of current customers will take us up on the sample test drive, and 20% of new customers will take us up on the sample test drive. But then we think that 12% of the current customers who take the test drive will buy a car, and that 20% of the new customers who take a test drive will buy a new car. The cost of mailing out the promotional materials, and probably mostly the cost is doing the research to decide which people to reach out to, perhaps, is $4 for current customers and $6 for new customers. Maybe you think the scenario should be that the costs are the same. Well, that could be, but we have things set up so that we can use different costs for when that's appropriate. And you could imagine that that might often be the case. The goal for management is to have at least 30,000 current customers take a test drive and 10,000 new customers. And then the number of current customers who take a test drive is supposed to be twice as many as the number of new customers who take a test drive. Because we want to encourage our loyal customers to keep coming back, I suppose, would be the thought there. You could easily imagine a scenario where it's the other way around. We want the number of new customers to be twice as many as the current customers. That's fine. It would not be a major change to what we're doing here to make it be that way. We have a budget of 1.2 million maximum that we could spend on the sending out of these materials. That does not include the cost of the test drives. So the question is, how many promotions should be sent to each group to maximize total sales? So to summarize some of the information here, we have two groups. We have current customers and we have new customers. And we know the percentage who we believe will respond to the promotion, and then the percentage who will actually purchase after having experienced the test drive. To set up a linear program, the first two questions we have to answer are, what should the variables be? And then what is the relationship between those variables and the objective function? In this case, we have two decision variables: how many promotions to send to current customers and how many send to new customers. So I'm going to let the letter C represent the number of current customers to reach out to, and N represent the number of new customers to reach out to. Pretty straightforward. Now, how do we write our objective function in terms of those two variables? Because our goal is to sell more cars, but we don't get to directly decide how many cars we sell. We just decided that the decisions that we can control are how many promotional offers to send out. So what's the connection between the promotional offers and the number of cars sold? Well, for current customers, 25% of them will take a test drive, and then 12% of those people will buy a car. Let me get my highlighter or my laser pointer going here. So on the current customers, 25% will take a test drive, and then 12% of those will actually buy a car. Then for the new customers, 20% of the people we contact will take a test drive, and 20% of those people will actually buy a car. So it's 20% of 20% of the number of new customers that we reach out to. So our objective function is to maximize 0.25 times 0.12 times C plus 0.2 times 0.2 times N. And then obviously there's no need to leave it looking messy like that or confusing like that. Just multiply 0.25 times 0.12, and we get that our goal is to maximize 0.03 C plus 0.04 N. And there aren't any other decimal places. That's all there is. So we defined our variables, and now we have written the objective function in terms of those two variables. Now let's look at the constraints. We know the cost to research and then send a promotional offer to current customers is $4, new customers are $6, and we have $1.2 million to spend. So this is pretty simple. We're paying $4 for every current customer we reach out to and $6 for every new customer we approach. So $4 times every current plus $6 times every new, $1.2 million. Just that easy. That was the easy one. Then next, let's look at management has specified a minimum of 30,000 current customers should take a test drive. That seems pretty reasonable. We have metrics of how effective we want this promotion to be. So is the goal that the number of current customers, C, should be greater than or equal to 30,000? Because it might kind of seem that way at first, except no, that's not what we want. C is the number of people we reach out to. And nobody told us you have to reach out to at least 30,000 current customers. No, they told us we want at least 30,000 current customers to take test drives. And take the number of current customers we reach out to, multiply that by 0.25, and that tells you the number of current customers who will, on average, take a test drive. So that gives us this constraint here. 0.25 C is greater than or equal to 30,000. Similarly, with the number of new customers who take a test drive, the goal we've been given is at least 10,000 new customers take a test drive. So again, you might think, oh, does this mean N is greater than or equal to 10,000? No. N is a number that we provide the opportunity to, the number that we reach out to. So 20% of them are going to take us up on the offer. So really, the number of new customer test drives that we see will be 0.2 times the number of new customers that we reached out to. So 0.2 times N, that has to be greater than or equal to 10,000. So this is how we take care of those two constraints. The last one we need to deal with here is this relationship between the two. And the goal we were given is that the number of current customers who test drive should be at least twice as big as the number of new customers. So current customer test drives should be greater than or equal to 2 times the number of new customer test drives. Now, we just saw on the last slide that the number of current people who take a test drive is 0.25 times C. The number of new customers who will take a test drive is 0.2 times N. And we want this 0.25 to be at least twice as big as 0.2N. The easy way to write this is 0.25C is greater than or equal to 2 times 0.2N. Hopefully that makes sense. Now I'm going to just simplify that, multiply that out. And then in order to have our linear program in standard form, we want to have all the variables over on the left-hand side of the inequality. So I'll write it as 0.25C minus 0.4N needs to be greater than or equal to 0. So that's our last constraint. That provides us the ratio that we were looking for between the two. And as I said earlier, you might feel when you're the decision maker someday that you want to reach out to twice as many new customers or 5 times as many new customers or whatever kinds of objectives you want to set. Just follow the same process and you can end up with a different constraint that represents your objectives. This then is the linear program. We're maximizing 0.03 times C plus 0.4N. Oops, I'm missing a 0. That should be point. Okay, I gotta fix this because otherwise. I guess I'll stop screen sharing. Didn't mean to do that, but so what happens when you edit slides? Sometimes you miss something, and this is just too important not to fix. Please hold. All right, there we go. 0.03 times C plus 0.04 times N. That's our objective function. Then subject to these constraints. 4C plus 6N is less than or equal to $1.2 million. 0.25C is greater than or equal to 30,000. 0.2N is greater than or equal to 10,000. 0.25C minus 0.4N is greater than or equal to 0. Now, what I did not write down there, but I perhaps should have, is that we do have non-negativity constraints here. The number of customers we reach out to cannot be less than 0. Either the current or the new customers cannot be negative. So if we formulate this in Excel, we would say, let's have a column for the current customers and a column for the new customers. And we sell 0.03 cars for every current customer we reach out to and 0.04 cars for every new customer that we reach out to. So that might make you think, oh, we should definitely be reaching out to the new customers. But then we have to think about the budget part. Current customers cost $4 to reach out to. New customers cost $6. So per dollar spent, current customers seem like a better buy without doing any math there. The yellow boxes is where I'm going to keep track of the number of current and new customers. And then the blue box, that's the objective function. That's the number of vehicles we would expect to sell as a result of these efforts. So we have the budget constraint. 4 times 225,000 plus 6 times 50,000 is 1.2 million, which is exactly satisfying the constraint. 0.25 times 225 gives us 56,000, which is greater than or equal to 30,000. 0.2 times 50,000 gives us 10,000, which is greater than or equal to 10,000. And then I should have written this as 0.25, but it showed up as 25%, but mathematically they're the same thing. Minus 0.4 times 50,000 is 36,000, which is definitely greater than or equal to 0. So we're ready to solve it. And this is, as you probably guessed, already the optimal answer. If we look at the answer report here, the number of cars sold would be 87,000. We're going to send 225,000 offers to current customers and 50,000 to new customers. And the budget constraint is binding. We've spent all of our available budget. The minimum number of test drives from current customers is not binding. We needed at least 30,000. We've got 56,000. So there's 26,000 slack in that. The minimum number of new test drives, we're at 10,000, which is what we were told we had to do. So that constraint is binding and there is no slack there. And then this last constraint is not as intuitive to read as the other ones, but it boils down to the left side has to be greater than or equal to 0, and the left side is 36,000. So we have a lot of slack there. That constraint is not binding. Which if you think about what that constraint said, it said that current has to be at least double, current test drives has to be double or equal to the, or greater than the number of new customer test drives. And we're looking at 56,000 new customer test drives and 56,000 current customer test drives and 10,000 new customers. So 56,000 is more than double 10,000. So that's our answer report telling us we expect to sell 8,750 cars by sending out offers to 225,000 current customers and 50,000 new customers. And the budget constraint is maxed out. We're doing just the bare minimum on the new customer constraint. And then the current test drives and that double ratio, those are not affecting our answer at this point. So let's look at the sensitivity report. So we're sending 225,000 offers to new customers and 50,000 to new customers. And the reduced cost is 0 because we're already optimal to have non-negative quantities for those. So really nothing to see there in the reduced cost column. The objective coefficient is 0.03. And if this 0.3 were to increase by a gazillion or a bazillion, this answer of the optimal thing to do would not change. But if this 0.03 were to decrease by not very much, this answer would change. And I know it's always confusing sometimes when we're dealing with decimal places, but this is 0.03, this is 0.003. So it's around 10% decrease. So if that objective coefficient, instead of being 0.03, if it was just a little bit less, the optimal decision of what to do would change. So we're going to explore that a little bit more in the next slide. Similarly, on the new customers, right now, 4% of them are going to buy a new car. If that decreased by as much as you want, the answer of what to do would not change. But if that increased just a little bit, then this wouldn't be optimal anymore. So when that's the case, that the allowable increase or allowable decrease is very small compared to the objective coefficient, that's a sign you want to step back and make sure that you are really confident about these numbers in the objective coefficient. How sensitive is your answer to changes in this? That's what this report is all about. On the constraints, the budget, we're maxing that out. If we had more budget, every dollar of budget that we would add would result in an increase in the objective function of 0.0075. So every additional dollar we spend results in 0.0075 more cars being sold. So the shadow price is not in terms of dollars here because our objective function is not in terms of dollars. Our objective function is the number of cars sold. So this tells us how much the objective function would change if we had more of this constraint. Minimum number of current people to take test drives. Again, the left side, our value is 56,000. The constraint was 30,000. So if you would change this 30,000, right now it has zero impact on the objective function. If you changed it enough, if you took it from 30,000 up to 56,250, if you increased it beyond that, then it would affect our answer and we'd have to change something. Number of new customers who have to go on test drives. We're doing 10,000, we're doing the bare minimum. And if you increase this, every unit that you increase this by is going to result in a decrease in the number of cars sold of 0.025, which seems like a small number, but it really is. If you think about how much profit there might be made from a car, it's a pretty big impact, actually. So just to kind of recap here, in the right side is the right side of the constraint, and the allowable increase and decreases are changes to those right-hand side, those constraints, and we're looking at how those changes affect our objective function, in this case, the number of cars that we sold. And like we just saw, increasing the budget, how much we can spend on this, every dollar we add would increase the number of cars sold by 0.0075, which again, doesn't seem like very much, but if you multiply that by 1,000, we go 1, 2, 3. So $1,000 more of advertising, we'd sell 7 more cars. I don't know how much money would we make off 7 more cars, more than $1,000? Well, I hope so. And then we talked about changing the number of current test drives. So I want to spend just a couple more minutes here as our last thing, talking about these changes to the objective function. Right now, it's 0.03. And like we said, it's 0.03. And if it increases, it doesn't change our answer. But if it decreases by only 0.003, that would change this answer. So decreasing from 0.03, decreasing it by 0.003 would take it down to 0.00266, which doesn't seem like that big of a decrease. And then similarly, with the number of new customers buying cars, right now we think it's 0.04. If that were to increase by 0.005, so it would go up to 0.0045, it's not that big a change. And so it's worth thinking about where those numbers come from. So that 0.25, this point, oh, yeah, oops, sorry about that. Oh, no. Sorry, got confused there for a second. The number of customers who are going to buy a car is 0.25 times 0.12. And that's how we got the 0.03. So okay, I got to fix that 3. How do I get that 3 in there? Sharing is sure. I think that's what threw me off. So what would have to change for that 0.03 to go down to 0.266? So if this 25% estimate is right, that 25% of our current customers are going to take us up on the offer and accept the sample, how much would this 12% have to change before the product of those two numbers would be 0.266? So if we, let me get my drawing implement. Here. So it's little. So right now this is 0.3. So if we assume that the 0.25 is correct, how much would we have to be off on the 0.12 before our answer would change? Before this 0.03 would go down to 0.027. So if we assume the 0.25 is right, so 0.25 times some new purchase rate, not 12%, but something else, call that X. So 0.25 times X is going to give us a total response rate of 0.027. If you just solve for X, X is 0.106. So if instead of being 12%, if the purchase rate is less than 10.6%, that means that this 0.03 would be smaller than 0.027. And that means that what we're doing right now is the wrong thing. So we think it's 12% of current customers who take a test drive will buy a car. But if it's not 12%, if it's only 10.6, our answer is not optimal. That's worth knowing, I think. Or looking at the other half of this number, if we assume that the 12% is correct, how wrong would the 25% have to be before we're doing the wrong thing? So again, we want, now X is going to be, instead of 25, what would it be? And so if we leave the 12% as correct, and we want the product to be 0.0266, so we solve for X, so X is 22.17. So if instead of 25, if it's 22.2 or 22.1, what we're doing is the wrong thing. So this helps us understand how confident we have to be in these numbers that we've gotten from our market research staff. So this is maybe a little more involved than most people would be interested to go, but I don't know. I think it's always valuable when you can sort of put everything together here and not just take numbers for granted. Somebody told me the number, use this number for this calculation, and I assume their number is correct, but it's worth knowing, like, if they're a little bit off, I'm doing the wrong thing over here. So then I might ask, okay, how confident are you in that number? So to summarize what we're doing here, we're deciding about how many resources to deploy to these two options. We're trying to maximize the number of units sold, and the number of units sold is equal to the number of people who were contacted or given this offer times the response rate times the purchase rate. And we had a constraint on the number of the total amount of resources we could spend in this effort. We had a goal of a minimum number of people to do test drives or to respond to the offer in each option. And then we had this constraint about the ratio between the two. So we wrote out the linear program. We solved it in Excel. We looked at the answer report and we looked at the solver report. I hope this was helpful. If you're still a little shaky, go back and watch it again, and ask me questions in class next time. Come on. And okay, wait, I need my pointer back. Can't get it back apparently. My computer's just working so hard.